So when we are talking about nuclear magnetic resonance, what's going to be important is having a charge, and when you spin a charge, it gives off a magnetic field. It sets up a magnet. And now this used to be an experiment that was done in middle school, which I don't think they do anymore, is if you take just a simple nail, just a metal nail, wrap a wire around it, we can create actually an electric magnet. We can create a magnet. Notice right now that this is not magnetic. It won't pick up the paper clip. We have our wire wrapped around the nail. Nail is not magnetic. But if you hook a battery to the wires, then our nail becomes a magnet as long as I keep holding the wires there. It will pick up the paperclip. So we can create a magnet simply by spinning a charge in the form of electrons, in a circle. So that's one thing that's going to be important in order to understand the theory behind nuclear magnetic resonance. Spinning a charge makes a magnet. And in this case, with the electromagnet, we're making electrons go in a circle, but that's a charge. They have a negative charge. The other thing is to recognize how magnets interact with each other. So what I have here is two magnets. They're just magnetic stir bars, a big one and a bigger one, much bigger than what you would use in lab. And so we have two magnets here, and they will interact with each other in space. That if I move one, it can make the other one move. So with space in between, the magnets feel each other. The other thing to recognize about these magnets is our magnetic field lines, and that the magnets like to be lined up within those lines with each other. So if I have this magnet and I put it over here at the end of the magnet, it's going to be lined up in this direction. They're lined up with each other. If I try to turn it the opposite direction, they repel each other. And it's trying to move away. And it wants to spin back. So when it's out here at the end, it wants to be aligned one direction, not the other. It spins back. But when I take this magnet that's now aligned the way it likes to be, and I try to put it alongside, it's going to want to rotate in the other direction. So what that says, the magnetic field lines go one direction through the magnet and the opposite direction around the sides. So that when it's happy this way, I try to put it over here, it's going to want to turn. So magnetic field lines go out, they turn around, they come back. Now the other thing about the magnet, as we said, they like to line up with each other. If I put this magnet here, it's nice and stable where it is. Now it's stable. If I try to turn it at all, it keeps trying to turn back. It always wants to go back, so it gets those magnetic field lines lined up. It's more stable that way. However, if I can turn it and get it exactly lined up wrong, it will stay there. That it will stay lined against the bigger magnet, even though it's not as stable. You do anything at all and it will go back to being more stable. So I can put energy in, get it to go to the state that's against the bigger magnet, and it will stay there, but it's going to want to relax back and give off energy. And this is basically what's going to happen in nuclear magnetic resonance. When we put in energy to flip something against the spin, it's going to relax back down, and we're going to record how much energy it gives off when it relaxes back.